Okay, now this is being recorded, and after our rounds of introduction and Q&A, and also the organizational issues about the lectures, I will start with the content of the lectures. Okay, so the first thing that I would like to um, discuss with you is a general introduction about what was known before the birth of quantum theory. Okay, so as you're going to see, physics before quantum theory will be called as classical physics, and then comes the quantum revolution. So I'm going to call what people knew before the birth of quantum mechanics as just classical physics. Namely, you all know the basics of classical mechanics, and in particular, this is encoded in the very basics as in Newtonian mechanics. So we learn the laws of mechanics as written by Newton. So the three laws and how to describe the motion of bodies according to these laws. And in particular, this can be summarized by Newton's equations of motion. I mean, the symbol of these laws, of course, it's not the only law, but you learn that if the net force, if you can compute the net force acting on a body, then this will be equal to the mass of this body times the acceleration. Okay. And if you can solve this equation, this is a differential equation. If you can solve this equation, then you can describe how the position of the body will change with respect to time. And this is what we spend, I mean, a large part of our physics education learning. Okay, we learn how to solve problems in Newtonian mechanics, and this is highly successful in the description of the motion of bodies. I mean, in our daily lives. Okay, and inside the Newtonian mechanics, I just decided to put it to highlight it. There is the theory of gravitation as written by Newton. So Newton just discovered that two massive bodies would attract each other according to his law of gravitation, which each mass attract each other with a force that is proportional to the product of the masses and inverse proportional to the squared of the distance between these bodies. Okay. With this knowledge, we can derive, for instance, how are the orbits of the planets in our solar system. And this is a huge success of Newtonian's theory. Then some of you probably heard about Lagrangian and Hamiltonian mechanics, which are just different formulations of classical mechanics. So these theories should be totally equivalent to Newtonian mechanics, but they are written in a different way. They are different mathematical formulations of the same theory. And of course, as being different mathematical description, they should not bring anything new from the point of view of results. But very often, when you formulate a problem with a different mathematical language, you gain a lot of insight to tackle problems that before you could not. So Lagrangian mechanics is, for instance, very suitable and very handy to describe systems with constraints. So if you want to describe the motion of a ball that is constrained to move on a surface, you use Lagrangian mechanics, and this problem is much easier addressed in the Lagrangian formalism than in the Newtonian formalism. Hamiltonian mechanics, on the other hand, is a formulation of classical mechanics that opens the door for quantum mechanics. As we're going to see, and you don't have to know Hamiltonian mechanics for this course, but as we're going to see, there is a quantity in the Hamiltonian description, which is called the Hamiltonian, that plays a central role in the description of physical systems. And this concept will have a quantum counterpart. And we're going to discuss that. Okay? Besides classical mechanics, we also have thermodynamics and classical statistical mechanics. So we have all these developments on the laws of thermodynamics, the concept of temperature, the concept of entropy, and the description of thermodynamical systems that were then understood from the microscopic point of view using classical statistical mechanics. So thermodynamics is a macroscopic theory, while classical statistical mechanics gives you the microscopic origin of the thermodynamical behavior. And finally, we have classical electrodynamics, which is the theory developed by Maxwell. Well, actually, some people get angry when we call just Maxwell's theory, because essentially the theory is summarized by what we call the Maxwell's equations. But each Maxwell equation was developed by a different physicist. What Maxwell did was to correct one of them and also to bring together the entire picture of what is known now as the electromagnetic field. Okay? And you can say that until the beginning of the 20th century, those physical topics as classical electrodynamics, thermodynamics, and statistical mechanics, and classical mechanics were the core of physics, and they seem to describe essentially everything that we had around us very well. Okay, so you didn't have to think hard in order to find an explanation to some phenomena. You just had to apply correctly one of these theories that I just described. However, this is how physics works. I mean, you start with a set of experiments. You try to find a theory that describes these sets of experiments, and you come out with a systematic description of that. Then you have a theory, and you push the boundaries of this theory. You try to see up to which scale this thing will work. And at some point, you can find a scale where this theory does not work anymore. And then you have to replace this theory by something more fundamental. And I mean, by looking at Maxwell's theory and Newtonian mechanics, people realized that there was a clash. And when I say people, I mean Albert Einstein. So this clash between Newtonian mechanics and Maxwell's theory that you're going probably to hear more about in the relativity course gave birth to what is called relativity. Okay, so essentially the result of this clash is that Newtonian mechanics is a good approximation for describing the motion of bodies that have speeds that are much lower than the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. So it's just much higher than any speed you can think in your regular life. And what turns out is that if you use Newtonian mechanics until this order of magnitude of speeds, you get results wrong. And as a consequence, Newtonian classical mechanics has to be replaced by what is called relativistic mechanics. So it's not that Newton's theory is wrong, it's just that Newton's theory is valid up to some speed. After that, things will get less and less correct. I mean, you can just compute, predict a trajectory of a body that moves with speed comparable to the speed of light using Newtonian mechanics, and you're going to fail. Okay, you have to use relativity. And then um, I want to remind you a bit of electromagnetic theory, because as I just said, it was the clash of Maxwell's theory with Newton's theory that gave birth to relativity. But also, it was the clash between Maxwell's theory and thermodynamics, okay, and the statistical mechanics, if you wish, that gave birth to the very first principles of quantum theory. So let me remind you about some aspects of Maxwell's equations. But before I start talking about that, I want to have feedback from you if you have learned about Maxwell's theory before. Can you tell me in the chat? Okay, so Prince says no. Okay, no, no. Okay, so okay, I I will try to give you an overview about Maxwell's theory. I mean, an overview is, in a sense, I will just try to have to make a sense of what is written in the board, and then you're going to understand what I mean by that. But also, before moving to that, are you familiar with, for instance, these vector operators, for instance, the divergence of a field or the curl of a field? Are you familiar with that? Yes, no, no. Okay, so I see that some of you know and some of you don't know. That's not a problem. It's just to gauge, I mean, my approach to the topic. Okay. Um, okay. So let me before. So I was showing you slide number 4, but before I have slide number 3 that is also important to mention. Um, As I said, it is precisely the clash between Maxwell's theory and thermodynamics slash statistical mechanics that will give birth to quantum theory. Okay? But what is the essential ingredient of this clash? So Maxwell wrote the equations that describe the dynamics of the electric field and the magnetic field generated by a distribution of charges and currents. Okay, so even if you don't know Maxwell's theory in depth, I am assuming that it is acceptable for you that if I have an electric charge, if I place an electric charge here, and then I come with another electric charge and place it in the neighborhood of this first electric charge, the second electric charge will feel the presence of this one. So it will be attracted, it will be repelled, whatever happens, this first charge impacts the region in the neighborhood of it. And we say that this first charge creates an electric field. Okay? Now, if I have a flow of charges in an organized fashion, they generate a current. A current is nothing but a flow of charges. And it is possible, doing some simple experiments, to understand that this flow of charges, namely the current, will create magnetic fields. Magnetic fields are precisely um, um, fields that are generated by the flow of charges. So a charge or a flow of charges can create an electric and a magnetic field. Okay? So what I'm saying here in simple words is that if you have an electric charge and if you move it around, it will create both electric and magnetic field. Are you following me? Just to have a feedback. Okay. What Maxwell predicted with his equations was the following. If I collect all my equations and look for solutions of these equations, one possible solution is that electric and magnetic field, they propagate throughout space in such a way that they form a wave. Okay? So electromagnetic field and so electric and magnetic field, they will be oscillating. So electric field will be oscillating like that. The magnetic field will be oscillating like that. And this thing will propagate throughout space. Okay, it's something very complicated to do with fingers, but you can try to imagine. The electric field is a vector, the magnetic field is a vector, and these vectors, they are oscillating in time and they propagate. Okay, this is a wave. Okay, you can think of it in analogy with the wave in the sea or the sound wave, but this is a wave formed by electric and magnetic fields. And Maxwell predicted that if you believe on the equations that describe the dynamics of the electric and magnetic fields generated by charges and currents, then you're going to produce electromagnetic waves. So what was very surprising is that starting in the 20th century, several experiments started to show that actually, if you treat light as a wave, okay, I forgot to mention that this electromagnetic wave, that you can think of it as something very, very crazy, is nothing but light. So light, for Maxwell, is an electromagnetic wave. But in the beginning of the 20th century, several experiments started to show that actually the wave picture of light was not sufficient to explain the outcomes of the experiment. So this is very disturbing because Maxwell's theory was working very well. I mean, all the development of optics was based on the fact that light was a wave and people could make very good predictions and, use the theory of waves applied to light in order to predict how a light wave will, diffract when passes through a hole and all that. And suddenly, some experiments started to challenge the picture of light as a wave. Before talking about these experiments, which are the roots of quantum mechanics, I want to talk about Maxwell's equations, just to give you some fresh, for some of you, review, for some of you, an introduction about what is behind this statement that light is a wave. So Maxwell's theory is summarized by these four equations here that you can write in the integral form. The integral form is on the left-hand side, or in the differential form that is written on the right-hand side. So just to explain the elements of these equations, E is the electric field, B is the magnetic field, um, Q is the charge inside the closed surface. This is an integral over a closed surface. Again, if you don't know the details, you don't have to worry about that. And by using vector calculus theorems, you can write this equation in differential form. So this operator here that is called nabla is nothing but a derivative. So if you don't know what nabla is, just think of it as a derivative, okay? And um, um, I is just the electric current, and these big phi's are the flux of the fields across a surface. But again, you don't have to know these details. I'm just making it fresh for you. Maxwell's theory then says the following. Electric fields can be created by charges, as you see here. So if I have a non-vanishing charge, I'll have a non-vanishing electric fields. Magnetic fields can be generated by currents, as you can see here. But also, Maxwell's theory says to you that an electric field can be generated by a variation of the magnetic field. So this is what is highly non-trivial. We always think about electric field as being generated by a set of charges. But Maxwell's theory says to you that you can generate an electric field by varying the magnetic field on time. And also you see here that a magnetic field can also be generated. So here I should have an E. The magnetic field can be generated by a variation in time of the electric field. So this is really a very conceptually a very interesting thing. If you change the magnetic field in time, you generate an electric field that will also change in time. And by Maxwell's equation, if you change the electric field in time, you're going to generate a magnetic field. So you start creating things out of the previous things. So you oscillate a magnetic field, you create an oscillating electric field that in turn will create an oscillating magnetic field, and so on and so forth. This is precisely why you have these electromagnetic waves. Okay, so you start oscillating electric fields, then you are going to have magnetic fields oscillating that will have electric fields oscillating and magnetic fields oscillating, and you create something that propagates throughout space, formed by electric and magnetic fields. Okay? And you see that to do so, you don't need charge and currents. If I turn off the charge and the current, I still have those terms that depend on the derivative of the flux of the fields, and these will generate for you the wave. Okay. So as I just wrote here, if you take your charge density, namely the charge per unit volume, and the density, the density of the current density, and take it to zero as well, you still have these non-trivial equations that you can combine one with the other and generate these two equations here. Okay? So by combining 1, 2, 3, and 4, I can generate this equation for the electric field and this equation for the magnetic field. Okay? These equations, maybe you are not familiar with that, but these equations are known in mathematics as the wave equation. Okay? So this equation describes things that behave like a wave. And in particular, the generic form of a wave equation is like this one. And you see that the coefficient that appears in front of the second derivative of the function f with respect to the time is 1 over v squared. And v is the speed of the wave. So compare this equation here with these equations here, this equation and this equation. You see that in front of the second order derivative of E and B with respect to time, I have mu zero and epsilon zero, which are constants that are introduced in Maxwell's theory to describe the strength of the electric magnetic interaction. So if this coefficient in front of d squared dt squared is 1 over v squared, then we can conclude that for the electromagnetic wave, the speed of propagation is 1 over mu zero epsilon zero rooted. And this has a value that is 3 times 10 to the 8 meters per second. That was something that we already talked before, which is nothing but the speed of light. And we call it c. Okay? So Maxwell's theory predicts that electromagnetic waves exist and that they propagate with the speed of light. So Maxwell predicts a speed. Okay? This is very non-intuitive. I mean, which theory predicts an absolute speed, right? Because this is a speed. Remember, when you measure a speed, you measure a speed with respect to some reference frame, right? There is no such a thing as a speed period. I mean, you have to measure the speed with respect to something. So there is a question, very good question, actually. So the question is, how these 4 equations are combined in order to get these 2 equations here. Well, it's a trick. I mean, it's a mathematical trick. You see that you have here equations that are, if you think of the nabla operator as being a derivative, these equations are just first order on the derivative. Namely, they contain just up to just to one derivative, right? There is no second derivatives acting on these equations, okay? And these equations are what we call coupled equations. Namely, you couple in the electric field equation, you see the magnetic field. And in the magnetic field equation, you see the electric field. But now, what I can do here is to take the derivative of these equations. So you increase the order of the derivative, okay? So this is a price to pay. You take the derivative, and when you take the derivative, for instance, if you hit this equation here with the nabla operator, if you take the curl of this equation, you are going to have the curl of B, or the divergence. If you hit this equation with the divergence, namely the nabla operator, you're going to have the divergence of B. But the divergence of B is just 0, okay? So you can, by acting with appropriate differential operators, you can use the previous equations, 1 and 2, and decouple the equations, okay? So you can find equations just for E and just for B. The price you pay for that is that in order to decouple them, you have to increase the order in the derivative. So now this equation becomes second order in the derivative, second order in the derivative, okay? But this is how you start from these 4 equations and get these 2 equations, okay? This will be listed as an optional exercise for you, okay? Further questions about that? Okay, so what we have seen up to page 4 of our lecture is that according to Maxwell's theory, light is an electromagnetic wave that propagates with speed being c. And let me just remark that this speed depends on the medium that light is propagating. So if light propagates in vacuum, the speed is c. But if light is propagating, for instance, in water, then the value of c will change. Okay? This is very important. Okay. Now let me. Okay. So there is a question. Can come again? What do you mean by that? You want to go back to the previous slide? Can I go on? You are going to have the PDF of this Blackboard. The last sentence I said is the following. If light propagates with speed c, namely 3 times t to the 8 meters per second in the vacuum, namely in empty space. However, if you just turn on a flashlight underwater, the speed of propagation will not be c, okay? It will be a different speed. So the speed depends on the medium that lights propagate. But apart from that, in a given medium, light will propagate with a fixed speed. Okay? Does it clarify? Okay, good. Okay, so next slide is where the mess starts. So let me begin with a description of what we're going to see, because this is exactly the first experiment that will reveal that light is not, or I mean, I have to rephrase that if you treat light as a wave and just use the classical theory of electromagnetism, then you cannot explain what you see in the lab, okay? And let me start by an introduction about what is the problem. So when a material is heated, namely, if you take a material and you put it on boiling water or whatever, the temperature of this material will increase, and this body will emit radiation. Just to make clear, when I say the word radiation, this is equivalent to emit electromagnetic wave, okay? And this radiation that is emitted by the body is known as thermal radiation. And you see that the word thermal here will connect back to thermodynamics and statistical mechanics. The body, the heated body, will emit this thermal radiation, but also if you send radiation towards the body will absorb radiation. Of course, the absorption is not perfect, so some of this radiation will be absorbed and some of this radiation will be reflected, okay? And this is very important because this is why we see things. For instance, I have this pen here, and you see this pen not because it is emitting radiation because it's heated. It is emitting radiation, thermal radiation, if you wish, but this is simply not visible to us. You see this pen because it reflects light, right? So there are lamps here in this room, and these lamps are throwing electromagnetic waves to this pen, and then they are reflected, and you see that. This is why you see the pen. If I turn off the light, I close the curtains, I make this completely dark, you're not going to see the pen because there is no more electromagnetic waves hitting the pen and reflecting to you. Okay, so it's very important for our vision that objects reflect radiation. And if you now think about this radiation that is emitted by a body, think of a lamp. If you take a lamp, you know that there is electric current going through it, and if you know that this object is emitting light, and you see that it emits light because there is electric current going through the lamp, hitting the lamp, and therefore the lamp becomes so warm that it emits thermal radiation in a region that we can see with our eyes. Okay, so the radiation is such that the frequency of the radiation is visible. So of course, if you sorry, if you turn off the light, then the lamp will cool down and it will stop emitting light. Okay, so it's crucial for how lamps works that they emit radiation with a visible frequency when they are heated. But of course, there are some objects that you can heat a lot and they will not emit visible radiation. And there are some materials that if you heat just a little bit, they will emit radiation. So the way that a body emits radiation highly depends on what this material is made of. Okay. However, there is a class of materials or a class of bodies that emit an universal radiation, thermal radiation. And this is what is known as black body. Well, they are known as black bodies in the sense that if you have an object that will absorb all radiation that hits it, so imagine that you have a ball and you revest this ball with some black tissue in such a way that all the radiation, all light that you send to this ball will be absorbed by it. So you can imagine that this ball is going to get heated and it will emit some radiation. And this radiation that is emitted by the ball is universal. Okay? This is a highly non-trivial statement because if you have a random material, since there is part of the radiation that is hitting the material and being reflected, then if you try to measure the radiation that is emitted or reflected by the body, you get these concepts intertwined. But now if you have a body that absorbs all the radiation that hits the body, if you measure some radiation coming out from this body, then it's radiation that is just purely thermal radiation emitted by the body. Okay? And this is what we call a black body. So by definition, a black body has a surface that absorbs all the radiation that hits it. So nothing is reflected. And if this body, can we see the black body? No. that's well, the black body will not be visible in the sense of I mean, if you can have a perfect black body. However, we can detect it by the thermal radiation that it emits. So our eyes are instruments that are limited to some frequencies. And we don't see light in all frequencies that it exists. So we don't see, for instance, infrared light. But if you go to some visible spectrum, then we start seeing things. But what I'm saying is that this body will emit radiation that is just thermal radiation, and therefore, typically, we don't see it, or however, as we're going to see, you can change the frequency that the thermal radiation is emitted. Okay, so let me see the questions, because I saw that. Is the amount of absorption same as the amount of not so in a black body you absorb everything, you don't reflect anything, so it's not the same. You simply absorb all the radiation that hits the body. Okay, so there is no reflection. And then there is another question. Hello, are we saying that in the absence of electromagnetic waves, object will be invisible? I would like to know, is it possible to create an object which will have zero effect? Okay, so this is a very good question. I'm saying that in order to see, uh, an object, you have to count on the fact that this object will reflect light, and light will hit your eyes, and that's how you see it. So it's not that the object is invisible if you're not shedding light on it, but it's just that your eyes, which are just instruments that measures light being reflected by an object, cannot detect it. So it's not that the object became invisible, it's just that your eyes are not able to see them. Just think about entering a dark room. If you enter a dark room at night, you're not going to see things, but doesn't mean that things are invisible. It's just that your eye is not able to detect them. Then there is another question. Does it mean that a body that emits universal radiation absorbs all radiation that hits it? So yes, what I'm saying is that if you have a body that absorbs all the radiation that hits this body, we call this a black body. And the radiation, the thermal radiation emitted by this body is universal. Okay? There is a question, very nice question. Are black holes also black bodies? Yes. And this is a fantastic property, because in principle, we would imagine that black holes just absorb everything around them, but they don't emit anything, because this would contradict the very concept of black holes. But when you take into account quantum effects, when you take into account quantum phenomena, quantum theory, quantum mechanics, you can show that actually black holes will emit a radiation, which is the so-called Hawking radiation, and it behaves like a black body radiation. Then there is another question. But after a given time, I think it reflects radiation. That's the point. By definition, no. The black body will not reflect any radiation. If you let it there, I mean, you can even destroy the material, of course. I mean, if you heat it too much. But by definition, the black body will not reflect any radiation. Can we create black body? Yes, I'm going to tell you how to create a black body probably tomorrow. But yes, you can. Examples of a black body. Yes. So one example, as I said, is if you pick up, for instance, a ball and you cover this ball with some black tissue that and then you have to be careful with the properties of this tissue, because you can have tissues that reflect more or less light, and then you have to find these tissues that are not so shiny. They really absorb everything. But of course, to have a perfect black body is challenging. So you're not going to find a body that, I mean, it's perfectly absorbing all the radiation that hits it, but actually is reflecting just a little bit of the radiation that hits it. But you can make it better and better. And also, for practical purposes, I will explain you how to create a black body, probably tomorrow. But you can do that. Yeah, I'm going to describe it tomorrow for you. More questions? Okay, so I'm just going to describe this plot here in this slide, and then I think we should stop to not be over time. And also, I don't want to rush with the explanation. So there is a question by Seth. So ideally, black bodies are not to reflect. So ideal black bodies are objects that reflect all the radiation that hits it. So it, sorry, not reflect, it absorbs all the radiation that hits it and do not reflect anything. Okay, this is the ideal black body. Okay. Okay, so this plot is a plot that um, I have a black body, okay, and I will measure the intensity of the radiation that is emitted by the body, the thermal radiation emitted by the body, as a function of the frequency. If you don't remember, the frequency measures how many times your wave oscillates per second. So your wave oscillates, namely, the wave has this behavior of going up, going down, and going up again. So this is one oscillation. Now this thing can take, a lot of oscillations per second, and the frequency will tell you how many times this thing will complete an oscillation in per second. This is the intensity of the radiation emitted by the body as a function of the frequency. And you can see that given a temperature T1, the intensity grows with the frequency. It hits a maximum point and then starts decreasing. Okay. Now I warm this body to a temperature T2 that is larger than the temperature T1, and I want to measure the intensity of the radiation emitted by the body. When I measure that, I see that the intensity has the very same qualitative behavior of the first one, with the difference that now the peak of this curve is shifted towards the right. Okay? And finally, if I increase even more the temperature, T3, then you see that the curve has again the same qualitative features, but the peak is even further to the right. So we are seeing that there is this behavior of growing, hitting a maximum and going to zero, growing, hitting a maximum and going to zero. And the only difference when I change the temperature is that the amplitude of these curves, they increase, and also the peak is shifted towards the right. This is an experimental outcome. So this is not a plot that you make out on a computer. This is something that you go to a lab and you measure, okay? So this is the result of measurements. I'm just drawing the results, but this you can measure. So there is a comment by Mahmoud saying, but we cannot create the ideal one. We cannot create the ideal one, but it doesn't mean that we cannot create a very good one. And in physics, this is what matters. I mean, in physics, typically, you have a mathematical model of something that is ideal, perfect, and so on. But when you go to the lab, you cannot reproduce the perfect one, but you can get a very good model that reproduces the perfect one up to the limitations of your devices that make the measurements. Seth asks, what causes the shift in the amplitude of the intensities? This is a very good question that we are going to address tomorrow, because as you're going to see, the classical theory of radiation simply does not explain these curves. Okay? So you have to change the way that you describe theoretically radiation in order to explain these peaks and where they sit. And these we're going to see tomorrow because I don't want to rush with that. Okay? But this question is central for the understanding the roots of quantum mechanics. Okay? So I will stop here. So I will stop at slide 5. And I don't want to rush with the material. The most important thing is that you learn the material. So please just ask questions. I'm happy that you asked a lot of questions today, and continuing doing so, tomorrow we are going to continue the discussion and show what actually is the classical prediction for that, and see how the classical picture fails, and you have to replace it by something completely new that is at the very heart of quantum mechanics. Okay? So I thank you very much for your attention. And I'm going to send you an email today with the link to the YouTube channel and also a link to a Google form because I want to know more about you. So I prepared some questions. It's not they are not scientific questions. These are personal questions that you are going to answer so that I can prepare better the next lectures according to what you know and what you don't know, so that I can insert extra material if needed, or I can remove material that I thought it will be useful, but you already know. Okay? So thank you very much. It was a pleasure. It was an honor. And I hope to see you tomorrow. Take care. And if you have questions, do not hesitate to write an email to me. Okay? So, bye-bye.
Bye.